Hello everyone, Chris Builder here. Before you watch the video from my class today, I need to talk directly to those of you who are not in my class and watch my instructional videos on YouTube. For those of you who do not know, I'm a professor in the Department of Statistics at the University of Nebraska-Lincoln. Administrators at my university have recommended the elimination of my department. All faculty, including me, will lose their jobs. I will not be able to post an instructional content like this to my YouTube channel anymore. And also, most students in the department will not be able to complete their degree programs here. It may seem strange or odd to you that a university would actually eliminate a Department of Statistics given the growing importance of statistics, data, and data science in general for the world. And we all feel exactly the same here. There is still a chance, though, that administrators will change their recommendation. If you like the content that I make available on YouTube, and if you think that statistics is important, please let my administrators know it. In the content description for this video, I've included information about how to send them a letter or just a small comment. With your help, I hope we can save the Department of Statistics, and if we are successful, I promise to continue posting these instructional videos. Thank you very much. The time is 12:30, so let's begin here. So today we will finish the graphics section. We'll get into the principal component analysis section, and actually between the two, we'll discuss the project some more. And just as another reminder, save our stats. Make sure you have your voice heard by submitting some feedback at that particular address there, if you have not already done it. One small update is that probably about, I think it was about 8 p.m. last night, a letter went to the Chancellor from the 6 affected departments that were deemed for elimination. A letter went to the Chancellor saying to stop this process, pause it, because some of the rules that are in place are not actually being followed by the university, which is disappointing. I haven't heard anything about what has happened from the Chancellor's office since that letter was sent last night. Another way to get your voice heard is that the Board of Regents will be having a meeting. They usually have monthly meetings. Their next meeting is on October 3rd, Friday. It's at UNMC. Obviously, that is a drive. I'm pretty sure some faculty from the Department of Statistics will be going there, but students are welcome to go as well. And one thing that anybody can do is that you can be request to be heard and to speak in front of the Board of Regents. Anybody who does that gets 3 minutes. Not much, but that is 3 minutes. But you have to make the request to do that 24 hours beforehand. If you go to the Board of Regents webpage, you'll see a way to actually do that. Do note that the Board of Regents usually meets here at Varner Hall, just right across from East Campus, but they do meet elsewhere at times. And unfortunately, in November, there's no meeting scheduled. The next meeting that would be scheduled is December 5th, which would be the date that the department would officially be eliminated if this keeps on going. So I think it's important to try to get this process stopped as soon as possible. If you want to do a road trip up to Omaha on Friday, head on over to UNMC and have your voice heard. Are there any questions? Okay. So we're going to talk about something called trellis plots, also known as co-plots, where the co stands for conditioning. Basically, what these plots allow you to do is plot multiple variables at the same time, where you focus on some specific variables, a subset of these variables, while conditioning on values of the other variables that are, let's say, in your data. Okay? So since you're conditioning on particular values, that's why this co-plot name also exists. But I think generally most people think of these as trellis plots. Now, I'll tell you a little bit of a story about when I first saw these. So back in the 90s, when I was in grad school, these plots were cutting edge. They were so cool. And the first time I actually saw these plots was during a dissertation defense for someone who was getting a statistics PhD. It was actually a friend of mine. And he was, for his dissertation, he had developed a particular statistic which he just simply called G, and he used that to do some kind of hypothesis test. And to illustrate just how good his statistic was in comparison to all the other methods out there, he used a trellis plot to do it. And when I saw this, again, the first time I ever saw this, like, wow, this plot really gets at the point. Otherwise, the way that people normally would present why their stuff is good wouldn't have told the story as well. Now, in the audience, I know most of you probably never went to a dissertation defense, but you can probably understand it's kind of a stressful situation. And in the audience, there's going to be students, faculty, and other people, because it's always open to the public. And in the audience, there was this kind of intimidating professor, statistics professor. I won't name names. And he asks the person who's defending his dissertation, did you name the statistics? Did you use the letter G here to name it after yourself? Because this PhD candidate, his last name began with the letter G. And this PhD candidate, the student, turns to this professor and says, no, I didn't name it after myself, which would have been a faux pas. I decided to use the letter G because it was good. Now this guy, this student who got his PhD, then he successfully defended, he is now the head of all the quantitative division of one of the largest pharmaceutical companies in the world. So it's interesting how things occur, how people progress. Okay. So to explain what a trellis plot is, imagine that we have three variables. And let's say we do a scatter plot between two of the variables. So let's call the variables x1 and x2. So we just do some kind of scatter plot. Okay? Now there's a third variable, and we like to somehow include that in the plot. And we've looked at ways to do that. But here's what a trellis plot does. It conditions on particular values of that third variable. Maybe, just to make things simple, let's say that this third variable is categorical in nature with levels, let's say A, B, and C. So what this plot does, it says, okay, for all the times that x3 is equal to A, let's do a scatter plot. Then we come over here. For all the times that x3 is equal to B, let's do a scatter plot. For all the times x3 is equal to C, we'll do a scatter plot. And then for all the times that x3 is equal to D, we'll do a scatter plot as well. Okay? And the way that I drew this plot here basically represents then that we have a positive trend for A and C for x3, and we have a negative trend for the other possible levels of x3. Now, if you were to just draw a plot of x1 versus x2 and ignore x3, what do you think would happen? Well, you just simply, you get a combination of all this, and you would miss probably what that trend is. And so that's the nice thing about a trellis plot. And so you can see why it's called a coplot, because we are conditioning on particular values of this third variable. But you also hopefully can see how it's called a trellis plot, because basically we're building like a trellis, like what you would see like in a garden. We have these boxes, we're stacking them on top of each other, and each of these boxes represents that we're conditioning on some other variables, while looking specifically at the relationship between particular variables within the box. And so that's where it gets its name. Let's see. Sorry, I thought there was one other thing I wanted to say about that. Oh yeah. So each of these boxes, they're not actually formally called boxes. They're called panels. So each of these areas where you're conditioning are called panels. Make sure you're familiar with that term. Now, most often when people introduce these plots, they always use one particular data set. There's a number of classic data sets in statistics, and this is one of them. This first appeared in, if you've heard of R.A. Fisher, which is an individual who did some of the pioneering work in statistics in the early 1900s up until probably about 1960. He had a book that went through many, many, many editions about statistics, and he had a particular data set in there that talked about the yield from a different number of varieties of barley, where these measurements were taken at a number of farms in Minnesota. And this is the plot. So we have barley yield on the x-axis. We have the different kinds of barley on the y-axis. And what's actually plotted is what's called a dot plot, where each of these dots corresponds to a specific year. So let's see, so for this farm that's in Morris, the yield for the treble variety in 1931 is located right here. So if you just simply, unfortunately it's hard to fit everything here, I simply go down, you can see the yield was, let's say, 40-something. And then for the year 1932, the yield was a little bit more. Do some erasing. Okay. It would be nice if I could fit all this on one screen here, but I can't. But notice we see some trends here. So in the first panel, 1931 had a higher yield. For the Wasaka, for Crookston, for University Farm, for Duluth, for Grand Rapids. And I thought this was all Minnesota. Maybe that's also in some other states there. Maybe like Grand Rapids, Michigan. But the weird one is this. This is in Morris, which is west of the Twin Cities, a little bit north. There's actually University of Minnesota Morris there. Notice how 1932 had a higher yield than 1931. And so the way that then the usefulness of trellis plots was always presented was that the fact that this happened was actually unknown before. No one had noticed this. But trellis plots allow you to see that. Also notice how you can see some trend across the different locations as well. But the Morris thing is what was really was of interest. And so for a very, very long time, this data set then was always used to say, there's the aha moment that we saw this. And this data had been used for so many years before, and no one had noticed it before until these trellis plots came about. But then the story gets a little bit more interesting. What people thought then from looking at this plot was that the Morris was actually an error. How could Morris for that particular year be different from all the rest? And so people thought, okay, this is the trellis plot helped us find the data entry error. Just flip the years. Then someone came around in 2013 and actually wrote a paper that appeared in American Statistician, and they investigated it a little bit further. And they found out that very likely it was actually not an error. If you want to know more about the reasons behind it, you can take a look at the paper. This individual, I can't remember what his first name is, but Wright, he actually works at a company called Corteva, which is just outside the Des Moines area, which deals with agricultural statistics. Or, well, he does agriculture statistics there. The whole company's dealing with like seeds and other stuff for agriculture. Okay, So how can we actually do these plots in R? Well, there is a function in the graphics package, which we've mostly been focusing on, called coplot, that will do this. But it doesn't work as well as functions in other packages. So this is then one of these examples where I say, okay, because it doesn't work as well, I'm going to actually use another package. The two main packages that people use for this purpose are ggplot2 and lattice. Sorry, but I'm going to focus on lattice. I think that it is easier to teach people for the first time to understand how these plots come about and how to actually work with the code using lattice than it is with ggplot2. So that's why I focus in on here. You know, for those of you who do have experience with the ggplot2 package, you're welcome to try to use it in various things that we do in this course. It's up to you. Okay. But I will tell you it's not necessarily easy to use either package to do these plots. Okay. So let's go to the serial data and do some illustrations about how to get these plots. Now to do this, we need to talk about different forms that our data is in, and then how to convert the data to a new form, because some functions require a particular data structure to it. And so let me go on over here to Tim. So let's say I have the following data frame that I create, where the first variable is, let's say, ID name. So some way for me to uniquely identify everyone. Maybe, you know, it could be like a person's name. And also maybe I have a numerical way to represent each person that's in my data set unique. So I have 3 observations for 3 people, let's say. I have also a person's age represented in the data set. But what I'm very interested in is as follows. I have a variable called time1 and time2. And what this basically means is that I'm observing some kind of response in every individual over time, one time point to a second time point. So in this particular case, we will often refer to this as longitudinal data. And you know, perhaps what I'm measuring here, notice it looks like it's a binary response, and it is, where maybe it's a 1 for if a person has a headache at a particular time point, a 0 if they don't have a headache. So you can think of it, maybe this is used in a clinical trial setting. So that's the structure of my data here. This structure is often referred to as a wide format. The reason being is because notice I have one variable time1, and then I keep on adding columns for every single time point, and so I'm making the data set wide. What I need to do is transform the data set into a long format instead, where what I want to do is put all this information about time 2 basically right under where time 1 ends, and then repeat information about each subject, repeat information about their age. So I want to go to a long format. Just out of curiosity, for those of you who have taken like the introduction to R class here, do you talk about wide and long formats and how to convert between the two? Okay, okay, good. I would imagine you're probably using something from the tidyverse to do that. I'm going to show you a way not to, but this is also, I believe, written by the same person who originated the tidyverse, Hadley Wickham. Okay, so to convert to a long format, I can use a function simply called reshape. So I'm going to reshape the data. And so I say, where's my data? I put then the variable that identifies everyone uniquely, id.name. Okay. I could also use id.number as well. And then I need to say, okay, well, which variables then are in the wide format? Which variables vary, in this case, over time? So that's where the name comes from. Then I need to say, well, what do I want to call now in this new long format? What do I want to call the variable that contains all the data? How about response? Because that's the response variable. Direction, meaning I want to go long. I can drop variables that I no longer need, meaning I can simply remove them. And then also a variable called, which I'm going to call, or a time variable, which I'm going to represent by time, and you'll see how that appears in the data frame as well. And so this is what I get. So we can see how everyone is uniquely identified. Notice how I have subject 1 there. I have subject 1 there as well. I have the corresponding ages for subject 1. Then the time var basically tells me I'm looking at the time where by default R assigns simply values of 1, 2, 3, 4 corresponding to each variable that now you are putting into this long format. And then the actual responses as well. Now over here, notice you don't see any kind of variable name above that. The reason being is because in data frames, in case you've never seen this before, you can actually assign a row label to every row in your data frame. Most of the time, it's not needed at all, so let's remove it. The quickest way to do that is to use the function row.names, so that everything wasn't set to. Row.name set to null, which means just simply get rid of everything. And then it just goes with the default labeling of 1, 2, 3, the row number. What's interesting is that this is one of the few places where when you make an assignment in R, that less than dash, where an actual function name can go on the left side. Normally it's always on the right side. This is one of the few places where you can do that. So now that's the long format. That's the format that I needed. If you want to see how to get back to the wide format, take a look at how I use reshape there. Okay, so I started off with this very simple data frame so that now we're going to go to the serial data and show how to use that. So let's again just take a look at the serial data. So notice with the serial data, I have 3 variables, sugar, fat, sodium. This will be like time 1, time 2, time 3 in the data frame that we just saw. Although I guess we didn't have time 3. Now my ID kind of variables correspond to serial. But I also want to keep track of the shelf, which is going to be like the age that we just saw. So to do this all, I use reshape. I say where my data is. My ID variable is ID. Okay, I end up using that. So I'm actually using ID rather than necessarily the serial name. I could use serial name as well. Actually, I could use the serial name only if each is uniquely. And if you remember, we saw that there is actually one serial that's actually repeated in the data set. Now there's a bunch of stuff that I don't need when I convert the data. So how about we use drop with those variables? Which are my main variables of interest? Sugar, fat, and sodium. They're going to be stacked on top of each other. The variable that's going to tell me, is it a sugar variable? Is it a fat variable? Is it a sugar response? Is it a fat response? Or is it a sodium response? I'm going to call that new variable content. The actual numerical values are going to be in a variable called amount. Direction equal long. So let's go ahead and do that. There we go. So notice the structure, notice the word content there for the variable name, notice the word amount there for the actual numerical values. Notice how I was able to keep shelf along as well. And if I do this with tail so that we can see the end of the data frame, We can see now I have the sodium values as well. So that's how you can make the conversion. Okay. But what I want to actually do is I want to do the first plot with just the standardized values. So I'm going to do exactly the same thing, but use z.serial, which contains all the standardized values. I won't go through the exact process that we had before, but this is what the actual data frame then looks like with the standardized values. Then to use the lattice function, I have to say library lattice. I am 95% confident that this package actually comes with a default installation of R. If not, of course, you can just simply download it from CRAN and install it. So the first graph that we're going to do in terms of a trellis plot is that we're going to do histograms, where we're going to do a histogram for each shelf and for each nutritional variable in terms of the sugar, fat, sodium. So we're going to actually condition on two variables, and what's actually going to be displayed is the amount variable, which contains the actual amount of sugar, actual amount of fat, actual amount of sodium. So to tell R, that's how we want to do it. We use a histogram function. The first argument is called x. Just basically, it's like a formula argument that you would see in other functions, but it's just simply called x. And we see x equal tilde, the amount, which contains the actual numerical value. Then we use a vertical line to say, I am going to condition on values of content and shelf. Notice how I say the word and there, and I use a plus sign. So similar to like you use the LM function to estimate a regression model with multiple variables, you would separate the variables with the plus sign. I say where my data is located. On my y-axis, I don't want counts, I want percentages. It's just going to be easier to work with, so that's why I did that. Then I need to, then I have an x-axis label, main axis label. Then I need to say, okay, I'm going to be generating actually 12 different histograms. How do I want them arranged? Do I want, let's say, one column, 12 rows? Or do I want, let's say, 4 rows, 3 columns? I decided to do the latter case. What's very, very odd here is that when I put the numbers 3 and 4 together, combine them together, please make note of this, 3 represents the columns. So the number of columns comes first, when normally we always put the number of rows first in anything else that we do with like matrices. So it's going to be a 3 by 4 grid or 3 by 4 trellis. And so this is what we get. And there's a plot. Let me jump back over here to Word so I can annotate on it. Okay. So notice on the x-axis, we have the standardized value. We have the percent on the y-axis. And notice how the way that this was arranged was so that each column was for sugar or sodium or fat. So I can make comparisons across the rows for the different shelves. And the default way that this is being done here is that you have basically a little line to indicate if you're shelf 1, 2, 3, and 4. So the closer you are to 4, the farther it is to the right. And so if we just focus on the sugar column here, remember the trends that we were seeing before? Sugar seem to have, shelf 2 tend to have a higher sugar content than the other shelves. Do we see that here? Yeah. How do you know that? Because of how all the histograms were arranged. I can actually see that. Indeed, that this is shifted, this histogram shifted in comparison to the other histograms. Okay? Now for sodium, maybe you could see it say the same thing about shelf 1 compared to the other shelves. For fat, it's a lot harder to make a judgment. So we see some trends. Now, something I want to mention, there was an error in the notes when I was going over my notes last night to prepare for today's class. The actual z.serial data frame, which contains all the standardized values that we've actually seen before in actually the previous section of the course, I had actually copied the output wrong. So make a note that what you see there in the notes is wrong. Just refer back to the previous set of notes, and you'll see the correct version of z.serial. Okay. Let's see if we can make this plot look a little bit nicer. And so now this is where things get more complicated, because now you're going against the defaults. And this happens with any kind of function, any kind of package. And so let's say that, I'm not a big fan of these lines representing the numerical values for shelf. Just tell me, is it shelf 1? Is it shelf 2? Actually tell me 1, 2, 3, 4. So how could we actually get that in there? Okay. Here's one way. So it's in this text is in red because it's not in the notes. Here's one way. This is the easiest way. I don't know why I did it the other way. So I have this data frame called z.serial.long that contains the long format of the data. What I could do is just simply create a new variable called shelf factor. Create that new variable in the way that we've seen before. And then say simply factor what's in the variable shelf. Shelf contains the numbers 1, 2, 3, 4. Now, R actually represents this shelf, or thinks that the shelf is a numerical value, which is it is. 1 is less than 2, is less than 3, is less than 4. But in order to get the actual number represented on the plot, is better to have R treat this as a categorical variable. And the way you do that is to use the factor function. And then I think we've seen that earlier in the semester. So that's what I do there. And so what I could do now is use a shelf.factor right where you see shelf.char for character, and everything will work. Now the way that I actually did in the notes is use essentially the way that you would do it in another statistical software package, which is not as efficient. For some reason, I decided to emulate that here. Maybe I was thinking, my mind was thinking in the language of another software package, and so that's why I did that here. It works, but maybe not as efficient. So what I could do is create a new data frame where I start with my original data frame and simply add another variable to it, shelf.char for character, where I say factor exactly what we saw before. This new variable, this new data frame, I decided to call it z.serial.long2, for the lack of a better name. And then I can use histogram again. The code is exactly the same, but now I use this new variable. And this is what I get. And you can see that indeed, now I have the numbers 1, 2, 3, 4 there. Still, I like to go maybe a little bit farther. Suppose I like to actually write out shelf equal for each of these panels. How would I do that? Well, there's a few different ways. The way that I have in the notes is that when I created this shelf.char variable, what I could do is instead of just only including shelf inside the factor, suppose I say paste shelf equal, in quotes, comma, everything that's in shelf. So let me actually show you the results of that. So PACE is a way to combine text, if you've never seen that before in R. And so notice how I've actually combined shelf equal with everything that was in the shelf variable. If I then combine this with factor, now we have R recognizes this as a categorical variable. Notice how it says the levels of the categorical variable at the very end. So if I now use that way of doing it, look what happens. I get something that looks even better. So this is a lot of steps. It's not the most interesting thing in the world here, but these are the extra steps that you often have to go through when you're doing plotting to get the plot to look nice, to get it presentable, to get it to a level that you're proud to have it in a report, or if you're, let's say, if you're doing some kind of research, you're proud to, let's say, have it being shown in a paper. You know, an editor of a journal, for those of you who are doing research, or maybe someday will actually, for those of you who are doing research now or will do research in the future, an editor of a journal might say, get it looking better. And these are often the steps that you need to take, and it often takes some time to figure out, how do I do that in a software package? So that's how you do it. Okay. Now things get even a little bit more complicated here. I'm going to touch on a few things to help you get started, but I know that things get complicated if you've never ever seen this package before. So let's say that I want to do a plot that looks like this. So I get back to my old way of displaying shelf, just because it was easier, because I'm not focusing on that right now. And let's say I want to put a density estimate on top of the histogram, because often we want to understand better what that histogram looks like. So how could I actually add that? Well, what you can do is use the argument called panel, where inside the panel you write a function about what do you actually want to appear in each panel. And so my function is, well, I don't have to name it. Function, parentheses, x. So I'm going to pass in some information called x, which actually we match up with what you have there. Then I say, first draw a histogram. And so I use the function panel.histogram, which actually is what's used to do all those panels. You just don't see it because you don't need it. Didn't need its precise control. And then I can use a function called panel.densityPlot that actually plots that smooth density on top of it. Then notice how I have a ... there. Does anyone know how the ... actually works in R? What does it do when you're dealing with writing functions? If you look at if you actually look at the code of any function, you will often see a ... listed in where you would expect the very last argument to be. Is it not talked about in 850 or what's the introduction to R class for undergraduates? I can't remember the number. 151. 151. Is the ... talked about? Okay. This is a very useful tool where you don't have to actually specify argument names, and you can just pass in a whole bunch of other information that may or may not be used in the function or by the function. And so basically what happens is with this here, all of these arguments and their values will be passed into it. Let me see if I can find another function in R real fast that has that same possibility. Yep. So here's the LM function. So I type LM so I can actually see the code associated with it. And notice we see that right there. So depending upon how you use LM, you might end up wanting to pass in more information. And so that's why that's there. Let's see, plot.default. Maybe that has it as well. Yep, right there. So plot that default. When you normally do a scatter plot, plot is a generic function. And if you're just working with a data frame, it will actually send you to plot that default and actually do that plot. Yeah, I don't think there is a plot.data.frame. Maybe I might be misspoken. Yeah. Let me just, sorry, now I'm getting into the weeds in terms of various interesting things about R. So notice when I type plot.data.frame, it says there is no function called that. How can I actually be for sure? You might stop there and say, well, okay, there's not a function, but there's another way to actually check. Does anyone? There's a function called getAnywhere. I have no idea what's going to happen here. Let's see. Aha! There is actually a function called plot.data.frame. Okay? I won't get into what that function is going to do, but very often when you're actually wanting to see actual code, and if you're dealing with generic and method functions, some method functions will be hidden to the user, which I wish R wouldn't do that. It started doing that about 15 years ago or so. And the reason why it was done was because they figured, okay, who's going to want to actually look at it? Most people will not. And so they started hiding functions from just simply typing the function name and printing it out. But you can always see if those hidden functions if you type getAnywhere with it. The way that I actually found out that was I had to submit a help request on, it still exists, there's an R listserv. I had to actually submit a help request because I couldn't find this function anymore because of these new things or new ways to organize stuff. And so I had then someone replied to me, which happened to be at the time one of the leaders in all of R. And so if you do a search for my name R, you might actually come across my post from many, many years ago. Okay. And so anyway, so what's going to happen is that this function is going to be run to do every single panel. And so this is how we get the plot. Now you could also do many other kinds of trellis plots in terms of what's in the panel. So suppose I want a scatter plot. I can use the function xy_plots to do that. And it has a syntax as you might expect. What's on your y-axis is sugar. What's on your x-axis is fat. We separate them with a tilde. And then let's say I want a condition on the actual shelf. And I illustrate here another way that you could get the shelf equal part on this, which is actually more convenient than what I did, where I actually put that factor paste part right inside there rather than actually creating a variable first. That came about from that. That can be very, very convenient. There's my data, my main title, my plot, and here is just the default layout of all the scatter plots by shelf. I could go a little bit further, make it fancier, use the panel argument, and once again, where I write a function where I'm going to pass in x, I'm going to pass in y, and R actually matches up y with this and x with that. It just happens to be because of how formulas work. For the panel, I want to start with an XY plot. How about if I put some grid lines on it? How about if I put a linear model on it, just a simple linear regression model? And indeed, this is what I get. There's another function called cloud, which allows you to do a 3D plot. It works very similar to what we just saw. Unfortunately, you can't go in there and rotate the axes like what we saw with the RGL package. Let's spend some time with this here. So far, we've looked at the relationship between like two variables, where we condition on a third variable that's categorical. It has a finite number of categories to it. What if, though, you want to condition on a continuous variable? what you can do is what's called form a shingle. That's the official name, which basically says, let's break up that continuous variable into categories. These categories can actually be overlapping. So you don't need to have a hard break between the categories. That can be helpful at times. So let me go over here to 10. So there's a function R called equal.count, which can be used to break a continuous variable up into categories. Which variable do I want to use in this particular case? Let's say it's the sodium variable. How many categories do I want? Let's say 3. What kind of overlap between the category? Let's say 10%. So if I do that, put it into sodium.group and take a look at sodium.group, this is what we get. So it gives you your data back, but it also shows you the categories, which is labeled by intervals. I'm not for sure why it would start at a negative value for the bottom category, but it does. Of course, you can't have a negative amount of sodium. So the first category goes up to about 5. Notice where the second category starts, a little bit under 5. That's how you get that overlap. Notice the counts, 14, 14, 15. So if you add that up, that is 43. But we actually have 40 cereals. So that's the reason why it's 43 is because we have that 10% overlap. So now we can use this sodium.group as a shingle for the trellis plot. You can even see levels. So you can see the different categories there. So let's use XY plot again, where I want sugar on my Y-axis, fat on my X-axis, given sodium.group. Let me just make sure that you understand. I didn't bring this up before. Why is a vertical line given? Or why am I vocalizing it as given? Remember in your first stat course, when you talk about conditional probabilities, you look at something like this, probability of A given B. The vertical line means given. That's why I'm using the word given when I vocalize it. Data equals serial. Groups. Factor shelf. It just helps me do some stuff here. There's actually I'm just showing you different arguments. There's auto.key, which allows you to put a legend on it, and then we have layout. Okay, let's actually go here. Where's that plot? There we go. So the reason, and I didn't explain that very well, the reason why I use the legend is because what I'm doing is actually allowing the points to be colorized by shelf. So shelf 1 would be what looks to be black. Shelf 2 represents orange. There's ways to control that a little bit further, but for what we actually end up doing, it's not going to be that big of a deal. If you're doing this outside this class, it would be important to start learning that stuff. But notice how the different shingles are represented in terms of the actual numerical values. Rather than actually typing out what the categories are, what you see here is a gray part of the trellis label, the panel label here, that shows, okay, these are the upper values of sodium, these are the middle, and you can see how the grayness kind of overlaps. And then these are the bottom values for sodium. Okay. The last thing I want to show you is actually a complicated trellis plot. You're never going to have to do one this complicated, but I just will show you this. This is a plot that I actually included in a statistical research paper, and you'll see that it was very helpful. It helped tell my story that I needed. And so what I did here was, I'll try to make this quick. I was trying to examine different hypothesis testing methods for a specific situation. Something that's very close to testing for independence in a contingency table, without getting into all the details. And the way that I did this was I performed what was called a Monte Carlo simulation study. We use frequently in research. Or basically what that meant was I'm going to simulate some data, in this case so that the null hypothesis is true, and I apply each of these testing methods to see if I reject or don't reject. Then I simulate another data set under the exact same settings where the null hypothesis is true, and I, for each of these 8 different hypothesis testing methods, check to see if I reject or don't reject. And I do this 500 times. Each time I'm using alpha equal 0.05. And so the basic definition that you would learn in intro stat course is, how often should I reject the null hypothesis incorrectly? 5% of the time, or 0.05 times 500, 25. And so what I can check then is actually calculate for each of the hypothesis testing method, do I actually get 5% or not? If I don't, that says the hypothesis testing method doesn't work as advertised. If I get something close to 5%, then I know it does work. But I understand that even with 500 data sets, I'm going to have a little bit of variability. So how much variability would I get? That's what's represented by this expression here. Does this expression look familiar at all to any of you? Where would you see it? Confidence interval for proportion. Essentially, this is what this is. I'm not using exactly the same way. I happen to know what the true proportion is that should happen if the methods work, which is 0.05, because that's what my alpha is. But what this does, it gives me a range where if I'm outside this range in terms of this estimated number of times I reject, if I'm outside that range, I should be really worried about the hypothesis testing method, and I probably shouldn't use it in practice. Okay, so then this is what my data looks like. I basically have formed a data set that has multivariate data in it. I have the simulation number, the simulated data set number, 1 through 500, or I'm sorry, excuse me. Let's actually ignore that for now. I have a number of settings. Sometimes I'm going to look at like a 2x2 contingency table. Sometimes I'm going to look at a 5x5, sometimes a 5x10 contingency table. So that's one of my variables of interest. I'm also going to control certain probabilities associated with this probability table. I'm sorry, this contingency table. And so sometimes they're going to be 0.6, 0.8. Sometimes it's going to be other numbers. I'm also going to control my sample size as well. Sometimes it's going to be 20. Sometimes it's going to be 100. Sometimes it's going to be 50. Sometimes it's going to be 200. Sometimes I'm going to control what's called an odds ratio as well. All of you know what an odds is. If you take the ratio of two of them, you have an odds ratio. And then finally, here are my statistical hypothesis testing methods. One's called RS, one's called Bond for Bonferroni, if you've heard of the Bonferroni method before. But there's going to be a total of 8 different methods. These are the things I want to summarize. I'm going to try to condition on some of these things. And so this is the actual plot that I put in the paper. Again, there's a lot of stuff going on here. We see a lot of uses of shingles. Let's just focus in on one here. Go one more time. Okay. This is basically like the dot plot that we saw with the barley data. Here are my 8 different hypothesis testing methods summarized. Let me actually go down a little bit here. Notice this is 0.05. I want these hypothesis testing methods to reject the null hypothesis 5% of the time, 0.05. I put green bands at 0.031 and 0.069. So if the actual estimated percentage of times that I reject HO is between these 2 bands, I'm good in terms of the hypothesis testing method. If it's outside, that method's not working right. So let's see what happens. So I have 2 different sample sizes summarized on this set of panels. Here, again, just a particular setting, odds ratio. And we can see that we have 2 hypothesis testing methods that are outside that band. Those methods are not working. You would not want to use those in practice. But we do see some that are working. We see one method that doesn't even, it's not even on the plot because it's even greater than the upper bound, which was, I think, 0.15 or 0.2. So it's not even on it. That one doesn't work either. And so notice what happens as my odds ratios increase from 2 to 25. What's happening to these particular methods? They are getting worse. And you can see that based upon how I've laid out the panels. That helps me tell my story in my paper that I wanted to illustrate. Don't use these methods. This NS stands for naive. The N stands for naive, so that was a good way for me to name it. What's actually working pretty well are these boot methods. Does anyone know why I use the word boot there? What do you think that corresponds to? If you don't know, that's fine. Have you ever heard of the bootstrap? These are bootstrap methods, and they work the best. So, anyway, so that's why I was able to tell my story then, to get what I was trying to get across in my paper by using this trellis plot. To actually construct it, basically what I did was I did essentially, this plot takes up a lot of memory. That's why you see it going up, it's disappearing. So I did a plot, did that plot, I did that plot, I did that plot, and I did that plot all separately, put them into PowerPoint, arranged them nicely, added in PowerPoint some text as well. That's how I did it. So if you want to construct a very complicated plot, don't think that you have to do it all in R. Take it into another software package and you can add stuff to it. You can arrange stuff. Okay, any questions about trellis plots? So in the actual project itself, now you have a way to do all of problem 1. So again, we have this NFL Combine data, and at the very end, I have a short question about trellis plots. And I ask you, would it be difficult to represent all the numerical values, numerical variables, which are a considerable number, on one trellis plot? If your answer is yes, tell me why. If your answer is no, construct the plot and interpret it. Hopefully you have an idea what the answer is. Now, there's a number of plots that we talked about in the graphics section, which are not represented in this project. You should still, on your own, play around with some of these plots and see how you can do them. So, for example, how could you construct a bubble plot for 3 of the numerical variables? Do that on your own. Problem number 2 now talks about using principal component analysis, or PCA, and that's our next topic. Go over to those notes. Any questions? Okay, so we got 15 minutes to talk about principal component analysis. This is an interesting statistical method. Similar to how we are currently using graphics, the purpose of this method is to give you an initial impression of your data. It is not the last statistical analysis that you would do for a data set. It's to give you an initial impression. But it's doing it in a numerical way versus a graphical way, although we'll incorporate graphics into this as well. And so imagine that you have a large number of variables, and they're all correlated or related to one another in some way. What principal component analysis does, it takes these, let's call them original variables, and transforms them into new variables. Where you hope, the goal is that these new variables are a smaller number of variables that you can use to understand your data, and there's these new variables allow you to understand your data and there's a smaller number of these new variables than what you originally started off with your original variables. So in other words, let's say you start off with 10 variables. It's hard to view the data in 10 dimensions. And we talked about like a parallel coordinates plot. That could be helpful. But if you could somehow view the data instead in 2 or 3 dimensions by creating these new variables and not lose much information at all about your data, well, of course, you would choose using just those 2 or 3 new variables. That's what principal component analysis allows you to do. These new variables are called principal components. And simply, these principal components are linear combinations of your original variables. That's it. So for example, we will look at this. With the serial data set, we will form a new variable, call it principal component, that's formed this way, where we take negative 0.667 times the original sugar variable, minus 0.5879 times the original fat variable, plus 0.4575 times the original sodium variable. This new variable is going to actually explain a lot of information about the original data. Now, it's not going to be enough to work with. We'll need at least one additional principal component that's going to be formed in a very similar manner to understand our data. Okay. So the objectives in a principal component analysis is to discover, let's say, the true dimension of your data, meaning the true number of variables that you really need. And so let's think of it like this, just to make sure this is clear. Let's say you have 2 variables. The Pearson correlation coefficient that you calculated for your sample was 0.99 between these 2 variables. So what that means is that, let's say they're x1 and x2. If I know x1, I pretty much know what x2 is as well, because I have such high positive correlation. So maybe instead what we could do is just look at one of those variables. Principal component analysis will give you a formal way to do that. Instead, let's say you have 2 variables that are not related at all, x1 and x2. Well, then principal component analysis is not going to help you at all, because it will still, you can still apply it to it. It will find new variables, but basically one of the variables will be very much exactly the same as x1, and the other variable will be exactly the same as x2. So this works if your data is correlated. The true dimension means the true number of variables that really will represent your data. Something else I forgot to mention too is that these new variables, called principal components that we form, have an interesting quality to them. They are actually uncorrelated. So if you were to find the Pearson correlation between, let's say, y1, which is your first principal component, y2, which is your second principal component, that Pearson correlation will be 0. So what that represents then is that they are representing distinct parts of your data, distinct parts of the information that your data is giving you. That's kind of cool. Now notice how we are forming linear combinations like this. So we could say that this y variable here, principal component, is a contrast between sodium and the sugar fat variables. Because I have a positive coefficient here, and I have negative coefficients there. And so we want to actually incorporate that interpretation into our analysis then. It's a contrast between the two. So if you've done an experimental design course where you've actually looked at contrasts before, this is kind of like that. It's not the same as doing, let's say, mu1 minus mu2, but it's kind of like that. Let's say instead, let me do a little bit of erasing. Let's say instead that for these coefficients on the original variables, let's say that one's negative 0.5 and one's positive 0.5. That's going to be very meaningful to us because what that's saying is that this variable is representing a contrast between sugar and sodium, where fat doesn't matter. And I would say exactly the same thing. Let's say this is negative 0.7 instead. It's still a contrast. Obviously, one's a little bit more weighted than the other, but it's still a contrast. That would be my interpretation. Now, in some cases, in many cases, I should say, this contrast, or whatever interpretation that you have, you could actually have, let's say, sorry, I keep on going back and forth. Maybe I might have 0.5 here, 0.6 here, 0.3 here, and it's all positive coefficients. Now that's like an overall measure of all the nutritional content. That will be an interpretation. Oftentimes, these kinds of interpretations will make sense relative to the underlying data problem that you're interested in. Sometimes, though, it may not. That's where, especially if let's say you're a statistician here, if you're working with a subject matter specialist for a particular area, let's say somebody who's in food science, you do this analysis and you can say to them, what do you think these principal components actually mean? Are they meaningful to you? They might say, well, yeah, they are. Other times they might say, I don't know at all. That can happen. But what we hope is that we do have some kind of meaning. We will actually, in the next section, look at a way where we can do something very similar to principal component analysis, but you have a chance, let's say, a higher chance of getting something that's meaningful relative to the original data problem. But that comes with issues. So some uses of principal component analysis. Data screening. So let's say that you have 10 variables. It might be difficult from looking at all those 10 variables to determine, are there any like maybe data entry errors that might come across as being found as outliers. And so if you're able to reduce the dimension of the data down to, let's say, 2 or 3, so you can do a scatter plot, you will be more easily see where there is an outlier. Where before, with 10 variables, it just might not be possible. It's going to be useful as an informal way to do what's called clustering, meaning that now again, since I only have, let's say, maybe hopefully just a few principal components, a few new variables, I could do like a scatter plot of them, and I could see through that scatter plot, let's say I have y1, y2, which is my 2 variables, maybe I see some points clustering like that. Then I can say, okay, those observations are similar to one another. And relative to the actual data problem itself, that might make sense. Where instead, if you had 10 variables, it would be hard to see that. So that's one use of principal component analysis. Now, at times, you want to actually use it to predict classifications as well. Let's say that I know particular observations, let's say, fit into groups 1, 2, and 3. It might be difficult to actually see how well a classification and prediction method works because you have so many independent variables. Plot the data with your principal components, then you might be able to actually see how it works, and you can see where let's say, maybe the model that you have makes an error. And there's also a particular application with regression. If you're interested, you can take a look at it. We won't actually touch on that in this class. We will touch on this and that as well. Okay. So to do principal component analysis, it's heavily focused on understanding the covariance matrix for your data. Well, yeah, I'll say the covariance matrix. So what we've called sigma. Now, note that if we have a covariance matrix, we can also find a correlation matrix. So there's actually 2 different ways to do principal component analysis. One with the covariance matrix and one with the correlation matrix, which we usually, like what we've seen is often referred to as P. I'm going to teach you the way to do it with the covariance matrix first, and this is very common. But most of the time, when you actually apply it in practice, you will use the correlation matrix instead, and there will be a specific reason that you'll see why, and you'll go, oh, yeah, that's why we went through that stuff in that data distributions and correlation section. That makes sense. So stay tuned for that part. First, we're going to talk about with respect to the covariance matrix. So we're going to find new variables that are linear combinations of our data, and the covariance matrix is going to help us do that. These new variables, called principal components, are going to be uncorrelated with one another, so they represent distinct parts of information in your data. Now, the very first principal component, the very first variable that you're going to form, is going to try to account for as much variability in the data as possible. The reason why we try to do that is that basically in statistics, variability means information. You know, if you've learned statistical methods in other classes where you try to explain the variation in the data, the more variation that you can explain, typically the better the statistical method performs, or the more information that it provides. For example, when you've done regression analysis, let's say you have a r-squared of 0.9, or you have a r-squared of 0.3. If you want your regression model to work, which would you prefer? The 0.9 part. Remember what r-squared measures? The percentage of variation that's explained by the regression model. Variability corresponds to information. We want to explain as much information as possible. And this first variable that you form is going to explain as much variability as possible. Each successive principal component is going to account for as much variability as possible after you account for all the other principal components that you form. So that second principal component, the second new variable, is going to account for as much of the variability that's remaining in the data as possible, accounting for the first, what it's explained, and the third in a similar way. So we're running out of a little bit of time. It's going to take me more than 4 minutes to get through how the actual math works. So this is like a cliffhanger, I guess you could say. You can read ahead if you want. But basically, we're going to be working with eigenvalues and eigenvectors associated with the covariance matrix. It's going to be interesting how it all works out. Okay, let me go back to this first document. So what's next for our class? I will have office hours. On Thursday, we will continue with principal component analysis. I don't think that we'll finish it, though. We will end up working with the goblet data that we briefly have seen before. And then looking further ahead, project number 1 is due on Thursday, October 9th at 5 p.m. And test number 2 is Thursday, October 23rd. Are there any questions? Okay, that's all for today.